Other questions?
More understanding of what is picture number.
Picture number. Well, the picture number is essentially how many delta betas you have introduced in the correlation function, right? How many delta betas and how many delta gammas? Because
or you can say phi momentum.
yeah, phi momentum, but I mean, if you don't, phi is something which came afterwards, right?
Like e to the I.
Yeah, e to the q phi is the picture number basically, right? So, but the point is, picture number was not there in the beta gamma system because beta and gamma carry picture number 0, right? So the picture number comes only after you do this bosonization, right? And there, in terms of beta and gamma, the operators which carry picture number are delta beta and delta gamma, right? So you can say that these measures basically how many delta betas and delta gammas you have.
So on a sphere, you will insert 3 delta gammas.
We'll see how many. I mean, the counting you are seeing because of the 3 C's. Why 3 delta gammas? No, we'll see because gamma is different, right? This is related to superconformal course.
Okay.
Right? So you have to check how many superconformal invariants you have, but you can also get it directly. That's like how many C's you have to insert, right? We could get by counting because SL2R has 3 generators, right? Or SL2C has 3 complex generators.
Right.
But you could also see by simply seeing what correlation function is well defined, right? Given the dimensions of C and B, if you recall, we saw that 1C is 0, 2C is 0, 3C can be non-zero. Right?
That's host number.
Host number, yeah.
Like host number because you have that anomaly. That
Exactly. Yeah.
That
So we'll do similar thing for picture number.
That was the fact that BCOP has the structure and we have this general conformal structure.
Exactly.
1 point to infinity.
Yeah.
Scalars over Z to the 4.
Yeah. So that led to the relation that you have to insert 3 C's and 3 C tildes. Exactly.
That will be true for gamma.
No, that will not be true for gamma. It will have some other counting which you'll do.
The same thing will
Similar thing will happen. Yeah. Yeah. But the point is there, the why 3 C's and 3 C tildes also have another interpretation. And that is that you have 3 conformal killing vectors, right? Which are gauge fixing, right? So 3 vertex operators have to be fixed, right? And that means that the diffeomorphism has to vanish at those 3 vertex operators, right?
Yeah.
So that's why you need 3 C's and 3 C tildes.
Okay. But
Right.
an analog of that superconformal is delta gamma.
Analog of that will be delta gamma.
Which are also 3 generators.
No, we'll see how many. That you have to see. We have to count, right? And why 3? How do you know it's 3? No. No, it's not that. It doesn't work that way. We'll see the counting.
But
Yeah.
there, in case of BC ghost, we also say that it's fixing the residual gauge.
Yes. So here also it is like fixing the residual.
But there is some like notion of moduli space there. I don't know if like here there will be.
Well, that is a super moduli space, but basically the way we'll do it is we'll integrate out all the fermionic moduli.
Okay.
Okay. Typically there will be super moduli, right? Some because there'll be a moduli and super moduli.
Right.
Okay. And then there'll be some residual gauge symmetries which have not been fixed, right? Which in this case are generated essentially by the G plus minus half. In NS sector, right, we have seen that on the vacuum, G half and G minus half don't annihilate the vacuum, right? So which are residual supersymmetries, just like L plus minus 1 and L0 are symmetries of the vacuum. Right? So those are the things you have to fix.
Central term in probably GG algebra will vanish.
Will vanish, yeah. Central term in GG algebra vanishes.
For plus minus.
Yeah, for plus minus half. Okay, but today we'll do the counting explicitly. Okay. So before that, let me remind you the bosonization rules. So beta of Z was del xi e to the minus phi, and gamma of Z was eta e to the phi, right? So from this, we can calculate the beta of Z e to the q phi of WOP. So this goes as Z minus W to the power Q times some operator. Let me call it some O1 plus Z minus W, 2 plus 1, O2, and so on. They're all at W. And similarly, gamma of Z of e to the q phi of W will be Z minus W to the minus Q times some other operator. Let me call it P1 of W plus Z minus W. Okay, it will have an expansion of this form. Is clear? So here I am using this OP that e to the q1 phi of Z e to the q2 phi of W is Z minus W to the power minus q1 q2 e to the power q1 plus q2 phi of W plus higher order terms. Okay, this is the OP that I had given last time. It is clear? Okay. So let's define the vacuum in the picture number Q simply as e to the q phi at 0 on the vacuum. Okay, you can also attach the K, the other level, the Fock momentum level, the usual momentum level, but that I'm not doing right now. Okay, let's just work in the ghost sector. So you define the vacuum at picture number Q as e to the q phi on 0 acting on the SL2R invariant vacuum. Call whatever, yeah, Q picture vacuum, right? It's still not the ground state, right? I mean, we will see that there can be lower L0 eigenvalue state. Okay, just like we saw that this itself is not the ground state, right? First of all, you can use act with C1, right? But you also saw that the actual L0 spectrum is unbounded from below, right? You can act many copies of gamma half, for example, this. This is the SL2R invariant object. Yeah.
At any point, will you take e to the q phi with q non-integer?
We'll see. We have to decide. No, we have to decide. I mean, we cannot, I can state it, right? But then have to justify it, right? So as we proceed, we'll justify it. And then it will also become clear what Qs will allow. Okay, you have to just be patient for a while, but we'll see. Not very far in the future. This is clear? Okay. So now, if we apply beta z on such thing, so beta z on Q, this will give you z to the Q times O1 plus z to the Q plus 1 on O2 and so on. But beta z has the expansion of beta n z to the power minus n minus half, or beta r z to the power minus r minus half. Right? Sorry, minus 3 half. Because beta has gone from 3 half. Pardon? R is half integer in the NS sector and integer in the Raman sector. Is that clear? So now you compare this. So this tells us, so R is integer for Raman sector and integer plus half for NS sector. right? So what does it say about Q? So now you can answer the question that you asked.
Q is half integer and then Q is integer.
Q is not half integer, it's R is half integer in the NS sector, right?
Oh,
So this power is integer in the NS sector, right? Okay.
Yeah.
So this means that Q is integer in the NS sector and it's integer plus half in the Raman sector. Right? And since you don't allow beta and gamma to have other mode expansions, right? Fractional mode expansions, we don't allow Q to be anything other than integer or half integer.
The interpretation that you said last time that e to the 5 is like Grassmann odd.
E to the 5 is Grassmann odd, yes.
That came from the fact that it has conformal dimension half integer.
Yes.
But if you take Q itself to be half integer, won't the conformal dimension become quarter?
Yeah, it will be. So the point is you have to combine that with a similar thing from the matter sector, and then the conformal dimension will again become something nice.
5 by 2, what should I think of it? Grassmann?
You shouldn't think of this either as Grassmann odd or Grassmann even. You should never you should never talk about it at all, right? So because these will be you remember that when you Raman sector, right? It's not just the beta gamma which gets twisted, also the size get twisted. Right? Exactly. Right? So the corresponding vertex operator, right?
Yeah.
Also has strange properties. Okay. But the product of that vertex operator with this e to the q5 with q odd. Or
The psi oscillators.
but not the vacuum of the Raman sector. We didn't even construct the vacuum of we constructed the vacuum state of the Raman sector, right? We didn't construct the operator that creates that state.
That is, yeah, I don't care about that. But I get an oscillator should have a clear Grassmann order.
Oscillators do, but not the spin field, which are creating Raman sector vacuum. We saw that Raman sector vacuum, Raman sector states cannot be created by oscillator action on the SL2 infinite vacuum, right?
Yeah, with the B0.
No, Raman sector vacuum cannot be created by using oscillators acting on the SL2 infinite vacuum. We got the Raman sector vacuum by doing the Clifford algebra quantization of the B0s, right? But the vacuum itself is not any B0 acting on the SL2 infinite vacuum. Right? So if you try to work with e to the 5 by 2, right, and try to manipulate it, you will always make mistake. Okay? So you cannot use e to the 5 by 2 by itself and declare it's Grassmann odd or Grassmann even and try to move it inside a correlation function. You have to always multiply it by the corresponding twisted operator in the matter from the matter sector, right? And then you can assign it an appropriate Grassmann parity. So don't try to think of e to the 5 by 2 either as Grassmann odd or Grassmann even. Yeah, we'll do about to actually construct the vertex operator. We can write in terms of abstract form, or we can do bosonization. Okay, and we'll see that these have strange conformal weight, as we said, neither half integer, not integer. Those will also have strange conformal weight, but when we add the two, then they will have proper conformal weight, right? Which allows you to give it an interpretation as appropriate Grassmann odd or Grassmann even operator. Okay, so don't try to assign Grassmann parity to the half phi. Okay, so a similar thing happens for gamma, right? Gamma of z on Q will be from this thing z to the minus Q, Q1. So it implies the same thing. Okay, because gamma of z, let me remind you, is gamma r z to the power minus r plus half. Okay, so again, in the ns sector, r is half integer. Okay, so q should be integer. And in the Ramond sector, r is integer, so q should be half integer. Right? The same conclusion as from the beta. Okay, but this also tells us something more. You see, here the expansion starts from z to the q and goes to higher powers of z. So this tells us that beta r on q should be 0 for r larger than minus q minus 3 half. That is true. Yeah. Okay, otherwise, you will get lower powers of z. Okay, the fact that you don't have z to the q minus 1 means, so r equal to minus q minus 3 half is okay. If r is minus q minus 3 half, then it will produce z to the q. Right? Z to the q term is present. Okay. But for any larger r, okay, you will get lower power of z, okay, which you don't have on the right hand side. These are leading power of z. Similarly, gamma r on q would be 0 for r larger than here, so r should be larger than q plus half.
Trying to make sense of z going to 0.
Yeah, z goes to, looking at the expansion in the z goes to 0 limit, right? Because this is valid only we have done the OP for small z, right? So you're looking at the z goes to 0 limit and trying to figure out what is the action of beta and gamma on these states. So from this we see that if we choose q to be minus 1, then beta r on minus 1 is 0 for r greater than minus half, and gamma r on minus 1 is 0 for r greater than minus half. Okay, and r is of course in the ns sector, r is half integer moded, right? So this says that r greater than minus half means r equal to half onwards, right? For r equal to half, beta half annihilates it, beta 3 half annihilates it. Similarly, gamma half annihilates it, gamma 3 half annihilates it, and so on. Is this clear? Pardon? I will make a point, but first you have to say if you agree with this or not. This is a special case of q equal to minus 1. The same statement that I gave here, right? I'm translating this as just substitute q equal to minus 1 and see what you get.
This is sector independent, right?
What?
MSR for both this sector independent.
Sector independent, but allowed values of q are of course different. So this is ns, because I have taken to be q equal to minus 1, right? So integer. R for r is q will half integer. So this is ns sector. Up to this point, it's sector independent. I mean, for any q, this is valid. Okay, so now what is the point I'm trying to make by this statement? Gamma half onwards annihilate the state, beta half onwards. Pardon? You cannot lower the energy by applying gamma half, right? Or by applying beta half. You remember the vacuum had the problem that you could apply gamma half and lower the L0 eigenvalue, right? And you can do it as many times as you want, right? What we see from here, that in picture number minus 1, L0 is bounded from below. Because you don't have any positive oscillator which doesn't annihilate the state. See, this means the gamma half on -1 is 0, right? And beta half on -1 is 0. You could apply, if you could apply this on the state, then you could lower L0 eigenvalue, right? But these are identically 0. Same is true for gamma 3 half and beta 3 half. Right? So by applying gamma and beta oscillators, you cannot lower the L0 eigenvalue of these states. Is this clear? So picture number -1 has this special feature that it is in this sector that the L0 eigenvalue is really bounded from below.
No other picture number this will happen.
In NS sector, no other picture number this will happen. Picture number 0, you have seen it doesn't happen. Right? If you go to other picture numbers, either beta or gamma will have an oscillator which will lower the energy, lower L0 eigenvalue.
So in picture number -1, the L0 eigenvalue of the states is bounded from below.
Yes.
You could have taken positive Q also.
You can take positive Q, gamma will improve, but beta will become worse. If you take Q equal to 1, right?
Yeah.
So then this tells us that beta R on 1 will be 0 for R larger than -5 half.
More things are
R, yeah, more beta is annihilated, but less gamma will annihilate. Yeah.
half.
Gamma half will still lower it.
So we have to take next. And what about -2? What is wrong with that?
If Q equal to -1, this will go wrong.
Beta half will not.
Yeah, beta half will not annihilate.
Beta gamma.
Gamma will be better, gamma will be fine, but beta half will keep, you can keep applying beta half. Beta half lowers, right? Beta with positive index will lower the L0 eigenvalue. Yeah, that I had a 0, but not this. What, L0 eigenvalue? Yeah, so L0 eigenvalue basically is the beta R has L0 eigenvalue minus R. Sorry, L0 eigenvalue minus R, yeah. Oh, -1 state we had counted last time. This is L0 eigenvalue half basically, right? E to the -5 has dimension half, right? We count.
This is Q.
Yeah, Q there, exactly. Yeah, that formula. I'll write it again, right, soon. So that formula gives you L0 eigenvalue half.
So this is trying to say that the picture number sector that you should be considering, which is bounded from below for the L0 eigenvalue, is the sector in which all states have a delta of gamma.
Yes, that's right. Which is also makes sense because the vertex operators, as we discussed, physical vertex operators, right, should have a delta of gamma attached to it, right? Because you want to put them at fixed points. Just like the physical vertex operators had C attached to them, right?
C corresponds to C1.
C corresponds to C1, yeah.
This what tells you that delta gamma is really e to the minus.
Well, I mean, we have already introduced it, e to the -5 is delta gamma, right? No, I mean, we could have called it e to the +5. Everything will change to Q will be -1 will become +1, right?
Oh, but OP was.
Yeah, I mean, all the OPs, etc. I mean, will change if we change that.
Picture number is very crucial.
Yeah, it's very crucial, but I should add that it is not that you cannot work in other picture numbers, right? You have to basically think of various formulas analytic continuation. I'll discuss this. It is true the L0 is not bounded from below. Right? So when you try to calculate, for example, a partition function or something, it's not strictly finite. Okay, you will get something like sum over n equal to 0 to infinity q to the -n, right? Where q is some number less than 1. This obviously doesn't make sense, right? It is divergent sum. But you can analytically continue for positive q, sorry, q larger than 1. And you can write this as 1 over 1 minus q inverse. Okay, which is minus q over 1 minus q. So if you're willing to do this, you can work in other picture numbers also. Okay. But if you are trying to do off-shell theory, right? In string field theory, picture number -1 is important because there you really want to work with off-shell objects, right? And you don't want off-shell string fields to have unbounded L0 eigenvalue.
Because in the beginning you had only beta and gamma.
Yes.
And then the bosonization gave you 3.
But before bosonization, I motivated by saying that you have to attach a delta gamma to the vertex, right?
Okay, and that had some hidden thing there.
That had some hidden to the -5. So this -1 picture is basically delta gamma.
Forget about theta, psi, beta phi, and just think about delta gamma, even when this argument can be.
If you work with delta gamma and beta and gamma, right? Beta gamma and delta beta. You can work everything, you can work with that.
Will give a state which in that sector there's no there's a lower boundary.
Exactly. Yeah. But it's a mess to work with those, right? Because the correlation functions and etc. are much harder. Okay? But we have seen, right? Xi and eta can be expressed in terms of the OPE of beta gamma and delta gamma, right? So in principle, you work with beta gamma and delta gamma, right? You don't have to talk about the Xi eta phi system. But it's much harder to do it that way. Anyway, this was just an aside, so let me.
Can you tell that how that analytic confirmation is related to the fact that my system is unbounded from below?
Yeah, so this is like q to the L0. Okay, and the fact that you have this q to the -n with n running from 1 to infinity, this is basically reflecting that there are L0 eigenvalues or arbitrary negative L0 eigenvalues. Right? And so that will be a divergent sum. From mod q greater than 1. Right? If you are willing to do that manipulation, then you can work with other picture numbers. Q equal to 1 you have what, right? Q equal to 1 is a singular object point in the model. I mean, Q equal to 1 is like degenerate torus or something, right? So you don't worry about. Q is like e to the 2 pi I tau. So Q equal to 1 is a tau going to 0, right? That's a singular torus.
Sorry, why? Okay, maybe I missed something in between. Why is Q equal
that Q and this Q are different.
Oh.
Yeah, this is X. Okay, let me. yeah, that Q and this Q are different. Yeah. Okay, is this clear? Okay, so in the Ramon sector also there are some picture numbers where things are okay. So if you take Q equal to -half, okay, what does it say? So beta R on -half is 0 for R greater than, if it's -half, is -1. And gamma R on -half is 0 for R greater than 0. No, Q is half integer in the Ramon sector. It's integer in the NS sector. Q is half integer, yeah. So I've taken Q equal to -half, right? Q is Z plus half. I've written as Z plus integer plus half. I mean, that you get just by comparing this expansion. Yeah, so here R is there, but there is a +3/2, right? And +half. So if R is, so in the Ramon sector, R is integer. Sorry, R is, yeah, so R is integer in the Ramon sector. So the expansion is half integer, right? So this has to be half integer. So what is this saying? Okay? This is saying that beta r acting on minus half, right, can be non-zero from r equal to 0 onwards, 0, 1, 2, etc. give a non-zero result, right? R greater than minus 1. So r equal to 0 is okay. Sorry, r equal to 0 vanishes, yeah. So r equal to minus 1. Yeah, those are okay, right? Minus 1, minus 2 are okay. 0, 1, 2, they all vanish, right? So you cannot lower energy that way. This one is saying that r equal to 0 doesn't annihilate it, gamma 0, right? It only vanishes for r greater than 0. So gamma 0 can act on the minus half state and give you something non-zero. Okay. You don't change the energy, right? But it will. This is telling us that even though it doesn't change the energy, you have infinite degeneracy. You can apply as many gamma 0 as you want. Okay. So that's the best you can do in Raman sector. Okay. So this has infinite degeneracy. From gamma 0 action. But no unbounded spectrum. And similarly for q equal to minus 3 half, we have beta r acting on minus 3 half is 0 for this term I think is r greater than 0, and gamma r acting on minus 3 half equal to 0 for r greater than minus 1. So let's see this. So r
Gamma 0 would minus half their eigenvalue of gamma 0.
minus,
I mean, not minus half. This state be eigenvector of gamma.
you can have it, but that will not be in eigenvalue, eigenstate of the ghost number. Ghost number. Gamma 0 carries ghost number, right? So if you want,
Ghost number operator will change.
yeah. So normally you try to take states to be eigenstates of the ghost number.
Trying to avoid the degeneracy.
No, it's okay. Degeneracy is okay. I mean, at least as long as the spectrum is not unbounded from below, it's.
Minus 2 also.
So let's look at q equal to minus 3 half here, right? So if q equal to minus 3 half, these become 0, right?
No,
And-
I'm talking about the minus.
Oh, minus half? Oh, for minus half, q is minus half, so this is r greater than 0. And if this is minus half, then this is half minus 3 half, right? Yeah.
Minus 3 by 2.
Pardon? Yeah, so for q equal to minus 3 half, 3 by 2, here again we have the same, it's bounded from below, right? No negative, no positive oscillators that doesn't annihilate it. But now beta 0 will create a degeneracy, right? Beta 0 acting on the state is not 0. So here, okay, so here gamma 0 acting on minus half is not 0. And beta 0 acting on minus 3 half is not 0.
It's the point that all these different states might be just QB exact and we don't
Yeah,
have-
so we are not talking about cohomology at all, right? Yeah, so in the cohomology, you will get finite number of states at a given mass level.
Yeah, but that can only happen. See, gamma 0, if it does not change energy,
Yeah,
it cannot always give new. I mean, otherwise you'll have in the massless sector also infinitely many states.
yeah, but gamma 0 doesn't commute with QB. So by applying gamma 0, you cannot generate new states in the QB cohomology. Yeah, not always. Is this clear?
So the one sector you have to work in picture number minus half or minus.
Yeah, you have to work in picture number minus half or minus 3. But as I said, that you don't have to if you are willing to do this analytic continuation. Okay, but these are the canonical picture numbers that one uses.
Right, picture number minus 3 half or minus half or both.
You can work with either. If you are doing just on-shell calculation, you can work with either. If you are trying to formulate a string field theory, then you need both.
The states in the theory, but throw them away unless there's some.
Yeah, we'll see what you mean by either. That also will come eventually. Okay, so next we will try to study some properties of the correlation functions. So let's consider, we are not trying to see, we are not trying to find the analog of the fact that we need 3 C's and 3 C tildes to get a non-zero correlation function. Okay, for the ghost sector that we found that we need 3 C's and 3 C tildes, right? Because otherwise you couldn't get a consistent correlation function. Okay? So you are going to repeat this for the xi eta phi system, right? And see what we can get. Okay. So we start with e to the q1 phi of z, e to the q2 phi of w as z minus w equal minus q1 q2 times e to the q1 plus q2 phi of w plus higher order terms. And now we take the vacuum expectation. Okay, vacuum expectation value always means expectation value in the SL2 or invariant vacuum. So this should be given by z minus w to the power minus q1 q2 times expectation value of e to the q1 plus q2 phi of w. But let's recall that this one has weight minus half q1 square minus q1. Okay, this is a formula we had found last time. So as z goes to infinity, this should go as z to the power minus twice this, right? Minus 2 times minus half q1 square minus q1. On the other hand, this form, as z goes to infinity, goes as z to the power minus 2, sorry, minus q1 cube. So this tells us that q1 q2 is minus q1 square minus 2q1, or equivalently q2 is minus q1 minus 2.
Only then will this correlator not vanish?
Pardon?
Only
Yeah, only then this correlator will not vanish.
they are-
Yeah, this 2-point function is equal to this, right? So if, of course, if both sides are 0, then there is a confusion, right? Then it's always consistent. But if these are both sides are not 0, right, then we need this relation. Q2 should be equal to minus Q1 minus 2, right? Which you can write also as Q1 plus Q2 as minus 2. Yeah, so I use this, okay? And now I am trying to check that as z goes to infinity, the behavior on this side agrees with the behavior on that side. because you know how it behaves as z goes to infinity, because this is the primary of dimension this, right? So as z goes to infinity, it should go z to the power minus twice this. No, in any correlation function, right? When other points are fixed, if you take z to infinity, it should go as this, right? So this, as z goes to infinity, should go as this. Now you take this has no z dependence, right? Yeah, but those other terms will be subleading, right? Yeah, okay. First of all, the point is OP by translation invariance doesn't depend on W. It depends only on the Z minus W. Okay. And there is only one scaling that you can have. You cannot have multiple scaling. This should have controls over it. That in order for this to be non-zero, this should have control at 0. Control at 0. Right?
I'm just saying that there are other terms in the expansion.
True. But one-point function of a field is 0 unless it has control at 0. This is general result in a CFT, you can see, right? In a vacuum, one-point function should have control at 0. If there are multiple terms, right, each of them cannot have control at 0. They have different control weights.
Right? One of them will have a generic.
Exactly. Okay.
Which one?
Whichever it is, right? I am trying to fix Q1 plus Q. Right? This part is not going to change anywhere. All of these other terms, right? That's why phi charge conservation. We have e to the Q1 plus Q2 phi.
Oh. Sorry. How are you concluding that?
Because there is a phi charge conservation, right? E to the Q1 phi times e to the Q2 phi, if you take the OP, okay, there will be e to the Q1 plus Q2 phi plus higher order terms. Right? Higher powers. So I'm just trying to fix Q1 plus Q2. Right? So for fixing Q1 plus Q2, you can just work with this leading term in the OP.
It cannot have e to the Q1 plus Q2 plus 1 by.
E to the power Q1 plus Q2 plus no, it can no. That expansion cannot have e to the Q1 plus Q2 because then that is inconsistent with the phi charge. You can have derivative of phi, multiplying it, right? Or derivative square of phi.
Multiplying e to the Q1 plus Q2.
Multiply e to the Q1 plus Q2 phi.
That will not be.
Yeah, meaning typically the one-point functions of those, they are non-trivial primaries, right? So they will vanish anywhere.
How do you get high charge conservation?
You take del phi, right? And take the OP, right? And that will tell you the phi charge is, if you take the OP of two things, right? You take the del phi, integrate it around the product of two operators, right? Then you can deform that contour and put it on individual operators, right? That tells us that in the OP of phi, e to the Q phi and Q1 phi and Q2 phi, right? Whatever things appear, right, should be always of the form e to the Q1 plus Q2 phi. But otherwise, if you integrate del phi around that contour, right, you will get a different answer. As Kaustubh was saying, suppose it has e to the Q1 plus Q2 plus 1 phi, right? That will not have the same residue as Q1 plus Q2, right? Whereas you can deform the del phi integral and put it on individually on e to the Q1 phi and e to the Q2 phi, and you will pick up Q1 plus Q2.
Separate from picture number conservation. Because picture number conservation has more things, right?
Picture number concept, the way you define xi and eta also carry picture number, right? But there is some combination of picture number and ghost number.
I see.
Translation of phi.
Translation of?
Phi. Invariance of translation.
Yeah, it is like translation of phi. Yeah.
For an endpoint function, you have summation of qi equals minus.
Yeah. For endpoint function, you have some qi equal to minus 2. Exactly.
Oh, sorry, I still didn't get that. Q1 plus Q2 is fine.
Yeah.
This is the thing we are looking at.
Yeah.
Other things are 0.
Exactly.
And now you want to say that they should go as fast as that.
Yeah. So the other things we can get by derivatives of this. Okay. If this one vanishes, then those derivatives will also vanish. right? So the point is the other things will be descendants of this. Okay. So if the primary correlation function vanishes, so if you are saying if this one vanishes and the other things contribute, right? Then
I think that this will vanish. I'm just saying the other things will come with the z minus w to the power something better.
but 2-point function cannot have different powers of z minus w. Just by the weight, right?
So the leading power should be this.
There's two, say 2-point function. In the OP, of course, you can have arbitrary power. 2-point function of two operators. Yeah, that just gives z minus w to the minus 2 delta. And that's you can say that that's another way of saying the same thing, right? That I'm saying here z to the minus 2h, right? But the 2-point function should go as z minus w to the minus 2 delta. Yeah, we can take the large element, which is this, yeah.
But RHS can have a sum of z minus w to the power something. Since you are expanding as a OP.
But the 2-point function will have to have a single power of z minus w, right?
Yeah, but at large z, why should it come from this leading term? That is not clear.
No, because 2-point function cannot have anything more than this. Because 2-point function is just a function of z minus w to some power, right? If there is another term here,
Plus the next term.
z minus w to the power this plus 1, right? That is inconsistent with the structure of the 2-point function. Because 2-point function of two primaries is z minus w to the minus 2 delta, right?
Delta is same.
Delta has to be the same,
Yeah, there is a.
otherwise it will vanish.
So you are saying.
So you cannot have z minus w to the minus 1 plus z minus w to the minus 2 and so on, right? I mean, that kind of structure doesn't exist for 2-point function. Higher point function, of course, you can have, right? So the higher order terms in the OP will contribute to higher point function, but not to 2-point function.
But you know, e to the q5 with e to the q5. That is what you.
E to the q1 5, e to the q2 5.
Delta for this is what? For the first operator, it's minus q1 square by 2.
Yeah.
Minus q2 square by 2. Now you are saying what?
Now I am saying that we compare this, the power that appears here, with the power that appears here.
Yeah. Just general 2-point function you are saying that has the structure, right? Just from confirming.
Yeah, so it has a structure z minus w to the power minus 2 minus half q1 square minus q1. Right?
This is at large z.
No, not a large z. 2-point function always has this structure. Pardon? But q2 has the same dimension as q1. And 2-point function of operator of dimension h1 and h2 is z minus w to the minus 2h1, and then h2 dimension has to be equal to the h1 dimension. No.
Or
Some other thing, yeah. Yeah, so q1 equal to qt is not consistent. Yeah, exactly. Yeah. Now, I don't even have to take larger limit. I'm simply saying that compare this power with this power. Right? Here I have just used the OP, is z minus w to the minus q1, q2. Yeah, that's the only non-zero thing that can contribute. Right? I now take this and compare the two. The power here with the power here. Okay, and that what gives you this.
so you are concluding q1 plus q2 minus.
Yes.
That's fine by me, but now you have to additionally also impose that q1 squared by 2 plus q1 equal to q2 squared by 2.
Automatic. Once this condition is satisfied, then you can check that the other condition is also.
That have two, I don't know, more than.
It has two solutions for a given q1. One is q1 equal to q2. The other one is this one.
Formula is 0 is what let's say have a 1.1.
Yeah.
Otherwise, this 2.1 would have been 0.
Exactly. Yeah. So what this is telling us is that e to the q5 of w is non-zero only if q is minus 2. Because that's the only conclusion that I want to make from that.
Primary profile which has 0 weight.
which has 0 weight. Well, identity also has 0 weight,
Q equals 0 would have been.
right? But that will be inconsistent with the OP that we have.
No. If I took Q1 equal to 1, then basically it will be Q1 Q5 and it will be Q5 2.1. That by translation, again you can argue it's Z minus W by 2 delta or minus 2 delta.
Yes.
Where delta is just minus Q square by 2 minus Q. But that will still vanish unless Q equal 1.
Q equal to minus 1, yes.
Minus.
Yeah. Pardon?
You have a primary.
Yeah.
2.1, then any primary in the CFT generally will have non-zero 2.1.
No. No. I mean, you can't consider. Yeah. Take del x1 with del x2. 2-point function.
Del x1.
With del x2.
Go talk to each other.
No. I'm saying same operator. E to the Q5 with E to the Q5.
Yeah.
So any given operator in CFT, I take it.
But E to the Q5 is not the conjugate of E to the Q5. If operator with its conjugate. If you take del x1 plus I del x2 with del x1 plus I del x2, this will vanish. Yeah, e to the ik dot x to the ik dot x will vanish, right? That is e to the ik dot x will e to the minus ik dot x, right? So the analog of this e to the minus ik dot x in this case is 2 minus q. So e to the q minus 2 minus q.
So why is this the background chart is kind of parameter like
No, it's fixed. Right? What is asking, see this fact that it is minus 2, right? This came from the central charge matching. I fixed the in the expression for T of Z, I fixed the coefficient of del square phi, right? Appropriately, so that the central charge of transfer to 13, so it matches with the beta gamma, right? What he is asking is that whether it is possible to take other central charges, change that parameter. If you change that parameter, then this Q will also change, right? The rule that we get here, because the control weight, the formula for the control weight will change, right? No, central charge has gone indirectly. The form of the energy momentum tensor, the del square phi coefficient, has gone into in the calculation of the H's, right?
Oh, I see. In the calculation of the weight.
Calculation of the weight, exactly, right?
That will have, if you put some arbitrary number in the R phi coupling there.
Exactly, linear term will change, right? And then this analysis will also change.
But we can do that, right?
You can do that, yeah.
But you don't want to do it because you want the central charge value to be 0.
Yeah, you want the beta gamma, you want to represent the beta gamma system, right? And to represent the beta gamma system, we need this particular central charge for phi.
No, whether like we could have changed the distribution of central charge among beta psi and phi. So why was that unique? We didn't done
Yeah, because I think the point is, as long as e to the minus phi you think of as delta gamma, right? It has a fixed control weight. You cannot really, play around with it, right? And that translates to what central charge you have for, yeah, for this phi. Because the way I introduced it looks somewhat ad hoc, that we had beta gamma and now we have phi xi eta. So why not distribute things between, maybe change the spin of xi eta and change the central charge of phi, right? You can make the total central charge agree that way. Okay? But ultimately, when you make when you state the relation between the beta gamma and the xi eta phi, then the phi's have definite meaning in terms of beta gamma, right? But e to the plus minus phi is basically delta beta and delta gamma, right? And that shows that you cannot just change things arbitrarily.
By solving that quadratic equation, you could have also got Q1 equal to 0, right? For Q1 equal to 0.
Yeah, Q1 equal to 0, but I fix my Q1. I can choose Q1 to be non-zero, right? Q1 is up to me.
Yeah, but sure. For non-zero, this condition is true.
Yeah.
But if Q1 is 0, that's just trivially true, right? Equation.
That's just identity.
Yeah, that's just identity.
Yeah, if Q1 is 0, this is identity, right? Then the other equation will not be true, right? Some other thing will go wrong.
So is it true that any correlator with picture number non-2
will vanish on the day. Any correlator with picture number non-2 will vanish, because you can always look at the OP, leading term in the OP, right? That has to be non-zero. on the sphere, and the leading term in the OPU will always give e to the q phi, where q is the total charge, right? Total sum of all the exponents. So if you take u1 e to the q1 phi, e to the q2 phi, e to the q3 phi, etc., then q1 plus q2 plus q3, everything has to add up to -2.
In usual CFD identity operator insertion, one point function will vanish.
Identity operator? Identity operator, one point function will not vanish.
So this is property of the vacuum, it seems that there it will vanish.
Yes.
It's
Because basically you say vacuum carries, there is a background charge, right? So you have to soak up that background charge up to
Background charge of the phi.
yeah, sometimes you can think of this as a charge sitting at infinity, right? Although that's not really not a good way of thinking about it, right? It's just there's an anomaly in the phi current, so the total phi charge is not conserved.
The background charge, I mean, the vacuum, since it has a delta gamma, it has a charge -1, right? The phi charge -1.
no, what I'm saying is, I mean, just as a CFT, phi CFT.
Hmm.
In phi CFT, identity with identity operator insertion, one point function
Vanish.
will vanish, and reason for that probably
Is the phi
Yeah.
charge, which is
that phi is not
Yeah.
possible.
Yeah,
But in
because
usually in CFTs, one point.
This collision function is in the SL2C vacuum.
SL2C vacuum, yeah. Everything is been done in the SL2C vacuum because this property holds only in the SL2C vacuum, right?
yes.
Yeah.
It's weird, but in general, in vacuum CFD, we just say only identity can take one part.
Hmm.
That statement is false. No?
That's false here. Identity has 0 vacuum expectation value.
I guess maybe if I think of
E to the -2 phi has
it's
also.
just an artifact of this phi CFT is
Oh, but it's
weird.
Is real.
It's weird. I mean.
Yeah, it's weird. Yeah, true. Yeah. Pardon?
There is another 0 dimension.
Yeah, there is another 0 dimension operator. And that is the one which cannot. -1 state norm is not 0.
Yeah, because it comes
Because you have two -1s, right? The identity has 0 expectation value. Between the SL2C infinite vacuum.
you put 0 and you put 0, that does not have minus.
Okay.
But if you put -1, then that happens.
That is -2. Yeah. That's another reason why -1 is good. And in the Ramon sector, you can see that -12 and -3/2 are conjugates. Right? The inner product between -12 and -3/2 is non-zero. The vacuum. Take the vacuum of -12, -3/2. That is non-zero. Yeah, that is in any sector also there are many such combinations, right? -2 and 0. That's also non-zero, right? So every picture number has a conjugate picture number with which it has a non-zero inner product. Yeah, well, so that's why I'm saying that -1 is a good thing, right? Why?
So log like Liouville, I mean, where
Yeah, it is like Liouville.
alpha q minus alpha.
Yeah, exactly. So this is like Liouville. Yeah, this is very much like Liouville.
Yeah, this is Liouville for q equal to.
Yeah, except that I mean you don't have that tachyon potential in this case, right? Liouville has a background tachyon potential switched on, right? That you don't have here.
Okay, here we just have the sort of QR phi down.
Yeah, exactly.
In case also identity has 0 expression because of the host, right?
Yeah. So once you include the host, this weird feature comes into play anyway, right? Or like in the C host, in the BC system, you need 3 Cs to get a non-zero expectation value, right? Yeah, here also is similar.
But there it's ghost number, here it is.
Yeah, it's fiction number, yeah. Phi charge. It's similar, right? So once you have this ghost system, this is very common that it will have such properties.
Is there a semi-classical way to argue like when you have QR phi term, we are bound to observe such a thing?
Yeah, there is a semi-classical way. It's basically similar to Liouville, meaning there is a charge non-conservation.
But you should be allowed to do that because eta psi phi is a fully quantum positionization, right? So there should not be a semi-classical way to argue against this.
No, but what he is asking is that not for this, but you can take this central charge to infinity in principle, right? Phi central charge. change the parameter to infinity. Yeah, right. In that limit, you may have an argument as to why this is the correct conservation.
As to why what?
Why you should have a non-conservation like this. Okay. See, he's asking this, he is saying that let's take a different theory, right? Where that parameter you take to infinity.
But you want the identity correlator. That's what you're looking for.
No, e to the q phi correlator. E to the minus q phi, minus 2, analog of the e to the minus 2 phi, right? Why is e to the minus 2 phi expectation value non-zero, right? You cannot understand semi-classically for this system. But if you take the central charge infinity limit, right, then there is a semi-classical description. Basically, you can think of this as in terms of a classical boson, right? And you can try to a free boson, yeah. In terms of some potential, yeah. See, there you can try to understand why this is the correct contribution.
Coupled to the Ritchie.
Yeah. Not free boson, semi-classical. You can use a classical equation to analyze that system, right? But I mean, there is no point in going into that because that's not a system we are dealing with anyway, right? So here you cannot apply that argument, right? But here I have given an argument, right? There is no, I mean, this you cannot get around. This is just a property of the system, right?
We just wanted to say that if you fix, let C float arbitrarily, this q equal minus 2 will change as a function.
Yeah.
And seeing going to infinity, this q will become 0.
No, it will not become 0.
Something.
Yeah, it will become something. It will become large.
Negative.
Yeah, some negative value, I mean, some large number, and that will be non-zero.
Okay, so the analogous statement to the bosonic case of there should be 3 C's and 3 C's and 3 C's and 3 C tildes is now just picture number minus 2. Is that it or is that more?
No, xi eta we have to check. Yeah? Xi eta we have not found. Done. So now we'll do the xi eta system.
Is this to say that there are 2 delta gammas required?
Yeah. Or if you use the phi, that 2 parts of e to the minus phi that is required to get a non-zero correlation function. Pardon?
Delta square of gamma.
No, I don't know. We do not have to put the 2 delta gammas on the same operator, right? Okay. So for xi eta system, let's start with xi of z, xi eta of w. So xi of z, eta of w, if you remember, is 1 over z minus w plus higher order terms. So this should be 1 over z minus w times the expectation value of the identity.
Already something you answered, but this psi eta OP we showed is that, I mean, if this is this, then the beta gamma OP is consistent. Right?
Yeah.
But this is the only way beta gamma OP is consistent.
Yeah, because once you fix the phi OP, phi you cannot change because e to the plus minus phi is delta gamma and delta beta, right? And I say their properties are fixed. So once you do that, then xi eta also gets fixed. Okay, but this one is not good, right? This cannot be non-zero, right? There are various ways to see it. First of all, xi has dimension 0, so as z goes to 0, this correlation function should go to a constant. Okay, it doesn't. And more generally, these two have different conformal weights. Xi has conformal at 0, eta has conformal at 1, right? So these 2-point function cannot be 0. Cannot be non-zero. Should be 0. Okay. So identity has 0 expectation, right? So, and by generalizing this, we can say that if you have equal number of xi's and etas, okay, you will always get 0. Equal number of xi's and etas, you can always take the leading OP, and that will vanish.
But this we already learned, right?
Learn from?
That the identity ka correlated is
No. Now we are for phi we know already that you have to put e to the minus 2 phi. Right?
yes, but
Even then, you put e to the minus 2 phi, doesn't matter. If you put e to the minus 2 phi of w, right? It has no OPU with this. So this will also be 0. Because e to the minus 2 phi of WOP, one-point function we said is non-zero only by ignoring the xi system, right? Just like in the bosonic string. We did the C first, we did the C tilde, right? And then we say that we need both C's and C tildes. Which one?
The minus
This is 0. Because we derived this by not including the xi system, right? It's like we said the product of C 3-point function, right? Is it 0 or non-zero? If we ignore the C tilde, then it is non-zero. Right? Yeah, but once you include the C tilde, we know that it is 0 because you also have to include 3 C tildes, right? So we analyze the phi system separately, e to the minus 2 phi we need. Right? Now you have to check if the xi conservation laws are obeyed. Same Hilbert space, yeah, but product Hilbert space, right? We can consider this as a product, and on the sphere, matter plus zeta plus phi. Yeah, because the way we have given the OPs, phi has no OP with xi or eta, right? They are really independent CFTs.
So for a correlator to be non-zero, you have to have picture number -2, but you should not have xi and eta
Equal.
number.
Yeah, you shouldn't have xi and eta number equal.
How many do you want?
Yeah, so the result is that you need one more xi compared to eta.
This is just at the same level as you saying the result is you need 3 C's and 3.
Yeah, well, just like we proved it there. We proved it, yeah. We started by putting more and more C's, and we found that once you have 3 C's, you can get a non-zero result.
But 4 C's we didn't prove that it's non-zero.
For 4 C's, you need a B. You can check that it is non-zero, that it is 0. If you just have 4 C's, right? The same argument will say that it doesn't work.
Yeah,
Right?
sure.
Yeah.
The way we did it is like for saying 2C0, we took a B, C, B and BC, and then took B3 OP.
Yeah.
That's what you're saying here.
Yeah. Let's say this one. This is non-zero, right? I'll write down an answer for this, which will satisfy all the consistency conditions. Yeah, so I have to be able to write an answer, right? Which satisfy all the correct asymptotics. Because that's the game we are playing, right? That you have to be able to write an answer which satisfies all the asymptotics. Right?
For the 2-point function, what was the asymptotic?
And okay, as z goes to infinity, this should go to a constant. Right? Then this one doesn't. As w goes to infinity, it should fall off as 1 over w square. Right? That one it doesn't. But even before that, right, this is a 2-point function of 2 different weights, right? So that you already know that it cannot be non-zero. Pardon? Because it has dimension 1, right? So as w goes to infinity, it falls off as 1 over z, 1 over w square, right? W to the minus 2h. So the fact that this is 0, you can see in many ways.
This goes as what? 1 by z is z3 to the 2.
Yeah. So this, how should it go? 1 over z3 to the 2 for large z, right? It should go as constant as z1 goes to infinity, constant as z2 goes to infinity, right? And it should have the right zeros and poles, right? For example, it should have a pole at z3 equal to z2 and at z3 equal to z1, right?
All the conformal invariance poles should be there.
Yeah, because the OP, from this OP, right? I'm going to give the result. It's z1 minus z2 up to a constant. Yes, it does look like that. And it does have 1-point function. So let's check if this is consistent, right? Z1 goes to infinity.
So the picture number has to be -2. Xi with the e to the -2.
Yeah, xi with e to the minus 2 phi will have 1 point. Yeah. Yeah.
Otherwise, so this is also 0.
Yeah, exactly. Right? So I'm already assuming that you have the e to the minus 2 phi somewhere, right? Yes.
There it should have been identity.
Yeah, keep
Yeah.
that by e to the minus 2.
Yeah, that I said just because I think Godwin was not very satisfied, right? Yeah.
Then what will be?
So the point is the right hand side is 0, left hand side is 0, right? Okay. So the right hand side also has to be 0, right? This is identity in the xi eta system, right? But what I'm saying is that if you think in terms of a product, right? E to the minus 2 phi you have to have anyway. Yeah, because any correlator will have a product of the phi correlator, product of the xi eta correlator, and the matter, right? And then the C's and B's, right? That way you can say, okay, every time I write anything, I have to put 3 C's and 3 C tildes, right? Instead of complain from there itself, right? Yeah, so of course it will have. Ultimately, you have to put 3 C's, 3 C tildes, e to the minus 2 phi, and whatever you are finding in the xi eta system. At this level, they are decoupled. So you are not, we're just talking independently of xi eta and phi and.
Those brackets are in the eta psi.
Yeah, in the eta psi system, exactly. Okay, so this has the correct structure, right? As Z1 goes to infinity, it goes to a constant, right? As Z2 goes to infinity, it goes to a constant. And as Z3 goes to infinity, it goes as 1 over Z3 square, right? It has a pole at Z2 equal to Z3, as you can see.
Maybe you can even decide the sign, overall sign.
Overall sign is a convention, right? Because if you now take the Z2 goes to Z3 limit, right? And compare, you see that xi, expectation value of xi of Z1 is 1. Because you pick up the residue as Z2 goes to Z3, right? And Z2 and Z3 are equal, so this cancels. Yes. So it should be antisymmetric under Z1, Z2 exchange. That's what you are saying, right? And it is, right? You can see. If you exchange Z1 and Z2, it's antisymmetric. Grassmann odd.
Could you remind me again that small argument that if W goes to, this is for any primary you're saying, right? If I have a primary insertion to the correlator, other points are fixed in the plane, and I take that point to infinity, and the conformal dimension is h.
Yeah.
The correlation function should go as 1 over
Z minus Z to the minus a to h, yeah.
Z 1 by Z
to h, yeah.
This came from
This came by mapping the whole correlation function by the inversion map. I of 1 over z. Yeah, exactly. VPZ conjugation, right? That takes the point at infinity to 0, right? And at 0 should be a regular point. So this correlation function as z goes to 0 should be finite, right? And that translates to this 1 over z to the 2h.
What comes with Z to the minus 2 delta factor?
Yeah, because that's an inversion transformation, right? Brought out the z to the minus 2h factor. Constant you cannot fix, right? That's the convention. That because you can see that the way you have written, right? Multiplying xi by a constant and eta by an opposite constant doesn't change anything, right? So that will fix to be 1 by convention.
That last lecture you said that we should not compute xi correlation.
We should not, yeah, exactly. So I'll also remind you soon that we should not compute xi correlation, but we can work with xi. I mean, xi is a system, right?
Sorry, why was that?
Because you work in a small Hilbert space, right? That because beta and gamma, right, are expressed in only terms of derivatives of xi. Okay? Which is okay. I mean, once I have given the xi correlation function, right, you can take derivatives to calculate the del xi correlation function, right? But there is a catch there, right? So I'll explain the catch, right? What the problem is. What? Because you just take Z2 to Z3, right? So by this OP, you should get 1 over Z2 minus Z3 times the 1 point function of xi, right? And that's what I did here. Z2 goes to Z3, and you get 1 over Z1 minus Z2, right?
We know the conformal weights, so we can write down the factor.
Yes.
Then what told you the constant is 0, not 0?
Oh, yeah.
Because a constant can be non-zero. That's what I'm saying.
Yeah.
It constant is not forced to be 0 by any OP or any conservation law, right?
Yeah. Can be 0, can be non-zero.
Yeah, true. But this is the only thing that can be non-zero.
So was 0, will the CFT be trivial?
Yeah, if this was 0, the CFT will be trivial, right? Because you can, it's like the C's, right? You found the 3 C's can be non-zero, right? And then if you add more C, again it will become 0, right? So more than, yeah.
I guess this defines the CFT, right? Whether you put a 0 there or not.
Yeah, if you put a 0 there, then you can say that, you can show that everything, all correlation functions will be 0.
That's a particular.
Well, but you don't want that, right? Then,
Yeah, you don't want
yeah,
that.
exactly, yeah.
This is the only thing that if you put it on 0, everything else will be 0.
Yeah, exactly. Right, which means equivalently, if you put this to be 0, right? Xi of Z1. If you put this to be 0, then everything will be 0 from there. Because if I'm saying that you need one more xi compared to eta, right? Then by taking OP of etas and xi's, you can always reduce it to one-point function of xi.
Del doesn't commute with the brackets.
Del does commute with the brackets.
Del psi correlator is not 0.
Del psi correlator is non. Del psi one-point function. It is 0 because it's independent of Z1, right?
No, you just said there's a catch there.
Yeah, I'll tell you what the catch is. The catch is that if you suppose you, as I said, that we cannot, you want to work with only del psi, right? Okay. So take del xi. You want to calculate del xi eta correlation function, right? That is 0. You can calculate it and it will be 0.
So just differentiate that with respect to 1.
Yeah, because this one I can also write as 1 over Z1 minus Z2 is Z1 minus Z3 minus Z2 minus Z3. So this is 1 over Z2 minus Z3 minus 1 over Z1 minus Z3, right? Okay, so if you take derivative with respect to Z1 and Z2, it is a 0. No. That doesn't have to be. Del xi of Z1, del xi of Z2 doesn't have to have 0. It's del xi of Z1, del xi of Z2, eta of Z3, right? That doesn't have to be 0, but it is 0. It doesn't follow just from antisymmetry.
In antisymmetric function of derivative, you take del Z1, del Z2 of that, which is
No. For C's, it is not 0, right? If you take C of Z1, C of Z2, C of Z3, it is non-zero. You can take the differentiate.
That's a more even with basic statement, right? If you take del 1, del 2 of some function of x1, x2, which is antisymmetric in x1, x2,
Yes.
that's not 0.
That's not 0. Del C of Z1, del C of Z2, C of Z3, right? Is not 0, I think.
okay, with the
No,
del
that's-
minus del by Z1 minus square.
No, that could be true, right? Del by del x1, del by del x2 of f of x1, x2, which is antisymmetric, okay? So then if you exchange x1 and x2, the del is just exchanged without a sign. The f exchanges with the sign, which basically gives you minus of the same thing. So that's 0.
No. Okay. Let's look at the, I don't think this is del C of Z1, del C of Z2, C of Z3.
Because I think one more derivative, if you take it, is supposed to be 1.
Yeah, exactly. If you take one more derivative of this, it is supposed to give 1, right? Del square C, del C, C should give you 1.
Why should you get 1?
Because del square C, del C is C minus 1, C0, C1. Right? You can put all of them on top of each other. See, this is okay. Let's see. The C of Z1, C of Z2, C of Z3 is Z1 minus Z2, Z2 minus Z3, Z1 minus Z3, right? Yeah. So if you take derivative of Z1, right, it gives you Z2 minus Z3 times Z1 minus Z3 plus Z2 minus Z3 times Z1 minus Z2. Okay. And now, so this is after del del Z1, right? And now you take del del Z2 of this. So this will give you Z1 minus Z3 plus this gives you Z1 minus Z2 and this gives us minus Z2 minus Z3. Yeah, so this is not 0, right? Z2 comes with a minus sign, 2 minus signs.
2Z1 minus 2.
Yeah, it's 2Z1 minus 2Z2.
Now you take any like these derivatives or even derivatives, you will get plus one.
Why is that constant analysis?
Why?
So what he was saying, I was also.
Okay, I'll leave it to you to figure out why that is not. That argument doesn't work. This is a clear demonstration that this is not 0, right? Yeah, you know.
Del by del x, del by del
He was
y.
saying f of x comma y is minus f of y comma x. Just take del x del y of both sides.
Yeah.
And then
What does it say? Del x del y of x comma y is equal to minus del x del y of y comma x. Yeah, exactly. That's what it says. That's okay. Yeah. Okay, now the question is what is the resolution, right? So we cannot work with this and calculate this thing, right? Okay. So the idea is that what we mean by working in the small Hilbert space, okay, is that if we try to start from here, okay, and calculate the correlation function of the del xi's and etas, okay, one xi you have to keep as xi. Okay, that is that. So what do we mean by this? So let me write this. So that product over I equal to 1 to n del xi zi I equal to 1 to n eta wi in the small Hilbert space is by definition xi of z naught product I equal to 1 to n del xi zi product I equal to 1 to n eta of wi in the large Hilbert space. Okay, this is non-zero. So one xi you have to keep without derivative. Okay. You can show that in this case, not only that this is non-zero, but this is independent of z naught. Okay, this correlation function doesn't depend on where you have placed z naught. So this is independent of z naught.
Ensured by the nature of beta.
Yeah, this will be ensured by the nature of the correlation function. So basically the product of in the small Hilbert, in the large Hilbert space, right? Any correlation function, so the product of xi's and product of etas, okay, one can figure out just from OP, right? Just the fact that the xi correlation function will have a 0 and xi eta will have a pole, right? Because that's, you can see that the way we wrote it, right? That for every pair of xi of z1, xi of z2, there should be a 0. And whenever there is eta xi, right, there should be poles. Right? So xi should have a 0, eta should have a 0, and xi eta should have a pole. Okay? That basically fixes the structure of the correlation function completely.
Is it like when
What do you mean by the subscript large really speaking? Because xi is not there in the. Oh, xi is there in large. Not
Yeah.
in small.
Xi is in large Hilbert space, not in the small Hilbert space.
Like small. With an extra xi.
We can extra xi 0. Right? So in the small correlator, the number of xi's and etas will be the same. Right? Because the large Hilbert space correlator, you need one more xi compared to eta. In the small Hilbert space correlator, you have equal number of xi's.
Yeah, anyway, referencing large.
No, you can stick to large, right? In fact, often it is useful to stick to large, but there are extra states which you don't include in the in your physical analysis of physical states.
But it will still be a just double copy, right?
No, it is not quite the double copy, right? Okay, you can say in some sense that has a Hilbert space, it will be double copy. You take any state in the small Hilbert space and multiply by xi0, it will give a state in large it will extend it to the large Hilbert space, right? But the actual correlation functions are quite different, right? Because this so okay, if you start with this, right? If you start with the product of the xi's, then even to show that this correlation function is independent of z0 is not trivial. You have to do some work to check that. Okay, but this is the way we will define the correlation functions in the small Hilbert space.
Up to this, it was fine. This people,
Up-
you showed that if you take two derivatives, then you will get 0.
Yes.
Then what is the next step?
Yeah. So then the large Hilbert space correlation function you cannot define by taking just derivatives of this.
Derivatives you are going to small.
Yeah. So sorry, small Hilbert space correlation cannot be obtained just by taking derivatives of this large Hilbert space, right? So what I'm saying is the small Hilbert space correlation functions are defined as taking the derivative of this large Hilbert space correlation function, except with one extra xi0. This I'll not prove, but you can prove it. Right? You can prove that this. So yeah. So how do I prove? You have to check that this doesn't depend on z0. Right? So this is something you can prove, right? From the structure of the large Hilbert space correlation function. Okay, this is just algebra, so but I'll not do that. Okay? It's just algebra because the large Hilbert space correlation functions are trivial to construct, right? Just from the zeros and poles, you can construct the numerators and denominator factors. Okay? But starting from there, to show that a correlation function like this independent of z0 right, is a little non-trivial. Because you have to make sure that you take a derivative on each of the other sides. Otherwise, it will not be true. Right? If any of the xi's are without derivative, then it will depend on z0. Right? So you have to apply derivative on each of the other sides, and then you can show that it will become independent of z0.
So now we need three C's, one guy.
One xi of z0 if you want to work in the
And
e to the minus 2 phi. To minus 2 phi, yes. Yeah. And that's also on the only on the sphere, on the plane. Higher genus, things will change. Just like in higher genus, even the number of the host number conservation itself changes, right?
the minus 2.
You get the 6g minus 6. Yeah, so we'll see. I mean, for the phi and xi eta remains the same. Yeah, there you have to need the more b's and c's than c's. Here you will need more picture number in the larger. E to the phi, yeah, e to the phi has picture number 1. So you'll need more e to the phi's. Okay, so I think I'll stop.
This number also saying like how many sites you have that in that.
How many?
Like this runs from 1 to n, right? Here also
Yeah, that because in the small Hilbert space, there is one more xi compact. Right?
Yeah. Triple function idea.
Yeah, but this is also true in the end, right? Because any arbitrary n-point function, you can by taking OPs,
We can reduce it to 3 point.
you can reduce to 1 point.
Yeah.
You can say that you'll get to one single xi.
Oh yeah.
So you'll always have one
xi more.
one xi, right? But so here in this form, we still have one xi, right?
Yeah.
Okay, so this
Yeah.
is non-zero
So
in
in
the
the
large.
large it will always have 1 5 more.
Yeah, in the large Hilbert space, you have always one side more. In the small Hilbert space, you just don't write that side because everything is independent of the side.
Okay, see.